Okay, so today we're going to do the last two topics of thermo. The second last topic is going to be called calorimetry. Okay, calorimetry. And basically what calorimetry allows us to do is it allows us to measure how much heat is transferred between two objects. Okay, so it's a measurement of heat flow, and if you remember, the symbol for heat is Q. So you're measuring Q. And we use something called a calorimeter in order to do that. We'll talk a little bit more about that in a second. But let's talk about one of the concepts that you need to know to do calorimetry. And it's something called heat capacity. Another term that is used for this is called specific heat. Okay, specific heat. Good. All right, so specific heat is very simple. It's basically the amount of energy that you need to raise the temperature of something by 1 Kelvin or 1 degree Celsius. Okay, so amount of heat, so amount of joules of energy that you need to raise the temperature of something by 1 degree Celsius. Okay, now every single substance has its own specific heat. So different objects heat up at different rates, which we kind of know from everyday life, right? Like metal heats up hotter, faster than water does, so on and so forth. So every substance has a different C value, the specific heat, and basically that's what we use in order to find out or to do calorimetry. All right, so this is the equation for specific heat right here. If you wanted to measure specific heat, it is Q, so the heat transfer divided by the mass, the grams of the substance, and the temperature change. So take a second to copy down that formula. All right, guys, so let's talk about how to use this equation. So what we're going to do first is we're going to calculate the specific heat of water. Okay, and it gives you this information right here. So it's very simple. You just plug and chug. So we are looking for specific heat. That means we're looking for C. So we're going to do C equals Q. Q is measured in joules, right? That's energy. So 209 joules goes on the top, divided by the mass of the substance, so 50 grams of water, so 50 grams goes on the bottom. And then the change in temperature is 1 Kelvin, so 1 Kelvin on the bottom. Okay, so pretty easy. Just plug and chug. And so that's going to be 209 divided by 50, and that's going to be 4.18. Okay, now the unit of measurement for specific heat is very specific, and so I'm going to go over what it is. It's going to be what you have on your fraction. So it's going to be joules per gram Kelvin. Okay, so if you're ever looking for specific heat, just make sure you're very wary of the units of measurement, okay, because it will matter. All right, so with that general concept of specific heat, now we're going to talk about calorimetry. And calorimetry is, again, where we figure out how much energy is transferred between two objects. And then just make sure you guys include the units of measurement for your final answer. If you're looking for a C, just look at the problem we just did. She's not here right now. Sorry. Okay, guys, so let's go over this problem. So super simple. You're looking for heat, so you're solving for Q. So we're going to leave that by itself. And then we just plug and chug our variable. So mass, 1,000 grams. So 1,000 grams. C is the specific heat of water, because we're looking at water. We just found it in the previous problem. So it'll be 4.18 joules per gram Kelvin. Okay, next part, we got 98 degrees Celsius minus 22 degrees Celsius, because this delta T, so whenever you have delta, that's change. So change in temperature is always going to be your final temperature minus your initial temperature. Okay, so we'll do 98 degrees Celsius minus 22 degrees Celsius. If you wanted to solve for, or change it to Kelvin, you can. But when it's the change, it's going to be the same change. The rate of change is going to be the same. So you don't have to change the Kelvin. But if you did, you'll still get the same answer. All right, so let's start plugging our values in. 98 minus 22, your delta T is going to be 76. Okay, and I'm going to change this to Kelvin now because that way we can cancel out our units, but it's just change. So Celsius and Kelvin are interchangeable when it comes to change. And then you have your 1,000 grams still, 4.18 joules per gram Kelvin. All right, let's start canceling our units of measurement before we do all of our math. You got grams right here and grams on the bottom of the fraction, so they cancel out. You have Kelvin on the bottom of the fraction and a Kelvin up here, so they cancel out. The only thing you're left with is joules, which is what you want because you're solving for heat, which is energy. Okay, so all we got to do now is plug it into the calculator. So you got 1,000 times 4.18 times 76, and then your answer is going to be this big number right here. And your final unit of measurement will be joules. Okay, so one of the most common calorimetry type problems that you will see is something called a constant pressure calorimeter, also called a coffee cup calorimeter. Now I'm going to explain what the concept is, so you guys don't need to copy this down yet. But let's go over what the concept of a coffee cup calorimeter is. All right, so we said calorimetry is you're calculating how much energy is exchanged between two objects, right? So what a coffee cup calorimeter does is it allows you to calculate that in kind of a closed environment. So usually you'll have this is your calorimeter, and it's going to be filled with water. Okay, so in here, we're going to label this as water. Okay, now the reason why we fill the calorimeter with water is because we know that water has a specific heat. Okay, 4.18 joules per gram Kelvin. Okay, so what you do in coffee cup calorimetry is you fill it with water and you just record the mass of the water. Okay, so whatever the mass of the water is, we record that. Okay. And then what the point of this is you're going to be finding how much heat is transferred by the object that you put in there into the water, and that allows you to calculate the heat transfer. So typically, this type of question, what it's usually going to ask you is it's going to ask you to find the specific heat of a metal. Okay, so that's going to be what the problems are going to ask you to find. They're going to ask you to find the specific heat of a metal. Sometimes they'll give you a table and tell you, once you find the specific heat, identify what metal you have. So what you do in this type of experiment is you basically just boil water in a different container, and you put the metal inside of the boiling water. Okay, so this is going to be our metal. Okay, and the reason why we do this is because boiling water has a very specific temperature, right? The boiling point of water is going to be 100 degrees Celsius. Okay, everybody following? Okay, so if you put a piece of metal in boiling water, what's the temperature of that metal going to become? Yeah, 100 degrees Celsius is the same, right? So what's going to happen is that you get the metal to a specific temperature, and that temperature of the metal is going to be 100 degrees Celsius because it's in this boiling water. Okay, and what you do after that is you take the metal out and you put it in your calorimeter. Okay, now if you put a super hot piece of metal, 100 degrees Celsius piece of metal in the water, what's going to happen is it's going to release energy into the water in the calorimeter, right? And so that's going to allow you to calculate the heat transfer, okay? And so let's start putting an equation to this now. So what's going to happen is the amount of the amount of energy, the heat that the water in the calorimeter absorbs is going to be equal to minus, so the amount of energy that the metal releases. Okay, so this is your initial equation. Okay, so just think about it logically. If the metal is giving energy to the water, the amount of energy the metal loses is the same amount of energy that the water absorbs, right? It's going into the water. So this equation is just basically describing that. It's basically describing that the heat that the water absorbs is equal to the heat the metal loses. Okay, that's what this equation represents. And what we do is we just expand this equation using the specific heat equation that we just talked about. So we said earlier that Q equals MCAT. So we just put in MCAT for the water and the metal, and that allows us to pretty much find all the variables that have to do with the water and the metal. So Q of the water becomes the mass of the water times the specific heat of water, the temperature change of water, and that is equal to negative the mass of the metal, the specific heat of the metal, and the temperature change of the metal. And that's pretty much the calculation that you will see for coffee cup calorimetry. This is the equation. This is ultimately the equation that you're going to use. And the way that we get this equation is from this right here, that the amount of energy the water absorbs is equal to the amount of energy that the metal releases. So basically, this is just combining this equation right here with the equation that we just learned about. Okay, now the reason why I wanted to go over how we get this equation is because you're not going to get this equation on your AP equation sheet. If you look at it, you have Q equals MCAT right here, right? But you don't have the equation for how it works with calorimetry, how it's equal to the energy the water absorbs and the metal releases. So you will have to remember this one right here to do calorimetry. Okay. All right, so what we're going to do is we're going to do a problem pretty much that describes this calorimetry. So I'm going to draw it for you guys, and I'm going to see if let's see if you guys can plug the numbers in on your own, okay? So it says that you're heating a 418 gram piece of metal. So you got a piece of metal and it weighs 418 grams. Okay. And you are heating it up in a water bath that is at 98 degrees Celsius. So you have it in a water bath and you're going to heat it till it gets to 98 degrees Celsius. Okay, so the mass of your metal, okay, so the mass of the metal is 418 grams, and the starting temperature of the metal is 98 degrees Celsius. Okay, so the initial temperature of the metal is 98 degrees Celsius. So far, so good? Okay. Next, you're going to transfer this into a coffee cup calorimeter. So we're going to have our calorimeter right here. I'll do this in blue. And remember, the coffee cup calorimeter is filled with water. And what you're doing is you're putting this piece of metal into the coffee cup calorimeter. And it tells you that inside of the coffee cup calorimeter, it contains 2,000 milliliters of water. Okay, so this time you're given volume, 2,000 milliliters of water. And that the initial temperature of the water is equal to 30 degrees Celsius. Okay, so what we're doing right now is we're just pulling the numbers out of the problem. And then it tells you, after you put the metal inside of the calorimeter, obviously once you put the metal in, energy is going to leave the metal, right, and go into the water around it. And then it tells you that the calorimeter, the temperature comes to equilibrium at 31.5 degrees Celsius. So what that tells us is that the final temperature of both the metal and the water, right, because they end up at the same temperature at the very end. So the final temperature of the metal and the water, it's going to equal 31.5 degrees Celsius. And then the question asks, based on this table, what is the identity of the metal? So in order to find the identity of the metal, basically what we are looking for is the specific heat of the metal. We are looking for C of the metal. That's what you're trying to find at the very end of your problem. All right, so that's all the information. I gave you the equation for how to solve this. So let me give you guys about a minute or two. See if you guys can plug in the values and solve. There is one value that you don't have right now because you're not going to be using volume, but the density will let you find the mass of the water. So see if you guys can try it out. I know I didn't teach this to you guys, but I want to see if see you guys kind of work through it, through the math. Use the equation we just had and see if you can plug in your variables to solve for the identity of the metal. So go ahead and try that out. We'll go over it in about a minute or two. All right, guys, let's start going over this. So before we start, I got the equations up there for you. So let's talk about this first. So we just said the energy the water absorbs is equal to the amount of energy the metal loses. So, right? So we used the Q equals MCAT, and we just expanded those two on both sides of the equal sign. So mass, specific heat, and temperature change of the water is equal to negative mass, specific heat, and temperature change of the metal. Okay, so this is the equation we just had. So we're going to start just by plugging in our values. So first thing we need is mass of water, which we don't have. However, we have the volume of water, right? And if you look at the density of water, it's 1 gram per milliliter. So just a little dimensional analysis. 1 milliliter is 1 gram. So it's just 1 to 1. So it'll just be 2,000 grams of water. Okay. So that's the mass of the water. Specific heat of the water, well, it's on our table right there, 4.18. So we're going to do 4.18. I'm going to omit the units of measurement just to save space, but it'll be the joules over grams Kelvin. Temperature change of the water is just going to be the final temperature of the water minus the initial temperature change of the water. So final temp is 31.5 minus 30. So the temperature change will be 1.5 degrees Celsius. Okay, so that is the water side. Everybody good with that? Okay. Let's go to the metal side. Metal is going to start with a negative sign. And then the mass of the metal, we said, is 418 grams. So 418 grams. We don't know the specific heat of the metal. That's what we're trying to find. So I'm going to write C, and I'll abbreviate it Cm just to show that it's a metal. Temperature change of the metal, I'm going to write this one out for you guys just so you have it. Temperature change is always final minus initial. So the final temp is 31.5. So 31.5 degrees Celsius minus 98 degrees Celsius. And this makes sense, right? Because the metal is losing, it's going down in temperature. So the temperature change has to be a negative number. And so you're going to get a negative number right here. So just keep that in mind. When you're doing calorimetry, you have to get a negative temperature or negative temperature change for the metal. So 31.5 minus 98, that'll give you negative 66.5. So right here will be negative 66.5 degrees Celsius. And that's the reason why we have a negative sign here. It is to show that the metal is losing energy, but it also pretty much fixes our calculations at the end. It gets rid of the negative right here. Okay. All right, so if you wanted to rearrange the equation to solve for C, you can do that, but I'm just going to straight solve it. So 2,000 times 4.18 times 1.5. And so on the left side of your equation, on the water side, you'll end up with 12,540. And then the grams and the Celsius will cancel out right here. And so it'll be joules right here. Okay, equals. And then on the right side, on the metal side, you're going to get 418 times negative 66.5. But the negative and the negative will cancel each other out. And so you'll end up on the right side with 27,797. And then it'll be grams degrees Celsius. And then you're multiplying that with the C of the metal. Okay, so to solve at the very end, you'll get 12,540 divided by 27,797. And you should get 0.451. So the C of the metal is going to equal 0.451, and you'll see that it's joules over grams degrees Celsius. Okay, so your final answer will be that the identity of this metal is iron, and that's going to be your answer. All right, let's move on to the last topic for the unit. The last topic for the unit is something called heat of formation and heat of vaporization. Now, this has different abbreviations. Heat of formation, we'll talk about that in a sec. The unit of measurement is usually going to be H, and then they also call it fusion, so H fuzz. And then vaporization, H vap. Okay, so that's the variables that we'll usually see for it. We'll talk about what that is in a second, but just write down the variables for now. Okay, so let's talk about what these things mean. Okay, so the heat of fusion is very simple. If we talk about it in the simplest terms, it's basically the joules of energy that you need to melt something. Okay, and melting, if we think about it, is when something goes from a solid to a liquid. Okay, I know that's very obvious, but just wanted to elaborate it because it'll be helpful for us as we're doing the math for this. And then vap is joules to boil something, and that's when you go from a liquid to a gas. Okay, so that's the two new variables that we will be using. All right, so we're going to take a look at these coordinates, and we'll talk about why this is important. So this is important because this is going to help us visualize the steps that we need to do for a calculation. Okay, so we're going to basically plot the energy that a substance has the temperature that a substance has based on how much energy you put in. So let's just think about this logically, okay? If you put energy into an object, what happens to the temperature? Yeah, it goes up, right? It goes higher. So the way that we would visualize that is as you put energy into something, the temperature goes up. Okay. And typically, I know that if you want to go into super technical stuff, there are other states of matter, but for our purposes, usually everything starts as a solid. Okay. All right, and what's going to happen is eventually, as you put more and more energy into a solid, it gets to a specific temperature point, and we call that the melting point. Okay, this is the temperature that an object starts to melt. Now, there's an interesting phenomenon once you hit the melting point. When an object gets to its melting point, even if you put energy into it, there's going to come a point where the temperature stops going up. Okay, this temperature is going to stop going up. And the reason why is because the energy is no longer being used to heat up the object. Instead, it's being used to break apart the interactions between the solid molecules. So in a solid, all the molecules are pretty much stuck together like this, right? Okay, now when you are heating it up as a solid, what you're doing is you're basically just making the solids vibrate faster. But once you get to the melting point, what you have to do is you need to break apart every single one of those solid interactions, the connections. And so that's what happens during the melting point. You're adding energy, but the temperature stops going up. And that's what we call the heat of fusion. Okay, it's the amount of energy required to break up those solid molecules. Yeah.
So like once it's broken up, then it's just like maintaining how it's like broken up.
Once it's broken up?
Like yeah, once it's broken up, it's just like keeping it like broken up.
No, once they're broken up, they're broken up. Yeah, you don't need to prevent them from getting back together. Yeah, so once they break up, once you break up every single one of the solids, then the temperature starts going up again. Yeah. Yeah, so the heat of fusion is the energy required to break all the solid connections. Basically, you're breaking all of the solids into liquid particles. Okay, so the energy is no longer used to raise the temperature. The energy is used to break up the solids from one another, the solid molecules. Okay, and then you get to the point where all of the molecules are liquid molecules. And obviously, as you heat up a liquid, the temperature is going to go up again. And then you guys can probably see what's going to happen next. Eventually, you get to a temperature point that we call the boiling point. And at the boiling point, the temperature stops going up again because what is happening is all the energy is being used to separate the liquid molecules into gas molecules. Okay, and that's the reason why when you're boiling water, even if the water is boiling, right, the temperature never gets past 212 degrees Fahrenheit or 100 Celsius. It's because all of the energy that you're putting in is being used to break the liquid into gas. And then once you get to everything becoming a gas, the temperature can start going up again. Okay, and that's pretty much what your chart should look like. So this is what the temperature energy coordinate looks like. Again, as you put energy in, temperature goes up until the energy starts being used to melt it. Temperature goes up as a liquid, and then all the energy is being used to boil it. And then once it's fully boiled, the gas can go up in temperature. Okay.
Does it ever keep the plasma?
It will, but that's different. Yeah. It's a different state of matter we're not going to talk about in this class. All right, couple things. So there are three different states of matter, right? You got your solid, your liquid, and, oh, I didn't write gas, and you got your gas. Important thing to note about all of these is that they all have their own specific heat value. Okay, so the C of the solid is going to be different than the C of the liquid and the C of the gas. They all have their own individual specific heats. Okay. So the types of questions that you will get regarding this topic is basically they're going to say, hey, you have 100 grams of ice at, I don't know, like negative 30 degrees. How much energy does it take to get it to water that's at 70 degrees? So you basically need to figure out how much energy it takes to get from this point to this point. Okay. Now, it's very simple. Every single one of these lines is its own step. So you got to do so if you're going from here to here, you got to do 1, 2, 3 calculations. Okay? And then God forbid if you get something from here to here, you have to do 1, 2, 3, 4, 5 calculations. So this is why this chart is helpful, is because it helps us see like how many calculations you need to do, and at the very end you add them all up. All right. And then another important thing that I forgot to mention is that every substance has its own boiling point and its own melting point. So 90% of the time, your problem is going to be water, so it's going to be at 0 degrees Celsius and 100 degrees Celsius. But if they said like, hey, sodium, then you're going to have a different melting point and a different boiling point. But you shouldn't see problems like that. So for example, water, the melting point is obviously 0. The heat of fusion is this value right here. The boiling point is this here, and then this here. And then you can see different substances have different boiling points, different melting points, different heat of fusions and whatnot. Okay, but anyway, it's easier if we do a problem. All right, so let's do this problem, and then I'll have you guys try a super hard one at the very end. Okay, so we're gonna calculate the amount of energy it takes to turn 14 grams of water that's at 20 degrees Celsius into 150 degrees Celsius steam. Okay, so before we start, what I want you guys to do is I want you guys to draw this coordinate on your paper. Again, this one can be a lot smaller because we're not going to be writing all over it. I want you guys to draw the coordinate with the lines that we just drew. And what I want you guys to do, before we do anything, is I want you to make 2 dots. I want you guys to make a dot for our starting position and a dot for our ending position based on what we talked about. So on your graph that you just drew, I want you to draw a dot for the starting position for this problem and the ending position for this problem. All right, guys, so let's do our, let's figure out where the starting and the ending dot are. So we said that this line, this first line right here, is when it's a solid. This first flat line is when you are melting. This is a liquid. This is when you're boiling. And this is when you have a gas. Okay, that's just summary of what we just talked about. So we are starting at 14 grams of water. So which of these lines should we have our starting dot at? Yeah, liquid, right? It's at 20 degrees Celsius, so it's probably going to be kind of closer to about a fifth up, right? So around here. So this is our start. And then our ending point is going to be 150 degrees Celsius steam. So where on the line should we put it? Gas, right? Somewhere around here. Okay, theoretically, the gas is going to go up for a while, so it doesn't really matter where you put it. Okay, and then if we wanted to label the boiling point and the melting point, it's because the melting point is at 0 degrees Celsius and the boiling point is at 100 degrees Celsius. Okay, so we just said the amount of lines that we cross is going to be the amount of calculations that we need. So we are going to need 1, 2, 3 calculations. So to solve this problem, we're going to have to do 3 separate calculations, and we just add it up at the very end. Okay? Everybody good? Okay. So let's do our first calculation. Now, the first calculation is actually pretty easy. It's what we already did. We're just going to use the specific heat formula. So Q equals MCAT. And specifically, what we're doing this for is, this is when we're heating the water. Okay, so we're doing 20 degrees Celsius water. And what we're doing is we're just going up to the boiling point. So this first calculation is this line right here, going from 20 degrees Celsius water to the boiling point. That's what our first calculation is going to be. And we're going to use Q equals MCAT. And I think you guys should be able to do this. So take about a minute or two, see if you guys can plug in your values for this and solve for the first step. What is the Q for the Q for taking 20 degrees Celsius water to the boiling point? All right, guys, let's go over the calcs. So we're looking for Q. The mass of water is 14 grams, right? So M is 14 grams. The specific heat of water is 4.18. Same thing as before, 4.18 joules per gram Kelvin. And the change in temperature is we are getting up. The final temperature for this step is 100 degrees, right? Because that's when it starts boiling. So our final temp is 100 degrees Celsius minus our starting temperature, which is 20 degrees Celsius. Okay, so just keep that in mind. The final part of the specific heat formula is delta T. It's the final minus initial. It's not just the starting. So it's final minus initial. All right, so let's cancel out our units of measurement first. Grams cancels out with grams. The Kelvin can cancel out the degrees Celsius because we're just talking about change. And so what you would punch into your calculator, is going to be 14 times 4.18 times 80. Okay, and that's going to give you 4,681.6. And what do we have left over? Joules. Okay. And so if we're going to put it on our graph, this step right here is going to require 4,681.6 joules. That's step 1. 2 more to go. All right, let's go to step 2 now. Step 2 is this line right here. Okay, and what did we talk about this line? We said that this line right here is going to represent how much energy it takes to boil all of our liquid. So this step is basically just boiling off everything that we have. Okay, the equation for this is a lot easier. It's going to be Q equals however much water we have. So I'm going to represent that with N. And it's going to be your delta H of vaporization. Okay, so N just represents how much you have. It could be grams, it could be moles. It's honestly going to depend on what units of measurement you get for your HVAP. Okay, so this step I'm going to do with you guys. All right, so if we take a look at our, let's look at our HVAP first. Our HVAP is 40.67 kilojoules per mole, right? I didn't do that on purpose, okay? Okay, 40.67 kilojoules per mole. Now, what do you notice about this unit of measurement that kind of stands out? It's per mole, right? Unfortunately, the problem does not give us moles of water. So what do we need to do in order to plug it into this equation? Yeah, we got to convert grams to moles. Okay, I'm going to do that with you guys, but that's a heads up I want to give you. Oftentimes, they try to trick you by giving you your HVAP as kilojoules per mole rather than per gram. Okay, so 14 grams of water, and the molar mass of water is 18 grams per 1 mole. Okay, so just keep that in mind. Units of measurement, I know that I'm being very specific about this, but it's because it's a very easy way for you to get tripped up and just lose sight of it as you're doing a lot of these problems. So 14 grams of water is going to be 0.78 moles of water. So that's going to be our N value right here. So 0.78 moles. And then we're just going to multiply that with the HVAP, 40.67 kilojoules per mole. On the top shelf. Thank you. Okay, now our answer is going to be 31.63. However, what is the unit of measurement? Kilojoules. That's another thing to keep in mind. Moles cancel out, and you get kilojoules. Now, what do you notice that's different about this than your previous answer? Yeah, it's kilojoules versus joules. And so when you add up these numbers, you can't do 4,600 plus 31. You have to convert one of them into the other. Now, we're going to have 2 steps that are joules, so let's just convert this to joules. You just move the decimal 3 times to the left. So 1, 2, 3 joules. And you're going to notice that this number is a lot bigger than this number. Okay, and that's another heads up I want to give you. It usually takes a lot more energy to boil everything than to heat up a liquid, which you should notice from your everyday life. If you're boiling water on a pot, it might take like 7 minutes to get it to boiling, right? But it'll take like an hour to get rid of all the water in the pot, right? It's because it requires so much more energy to boil off something than to just heat it up. Okay, so chemistry is applicable. Next time you boil water, you're going to be thinking about this. Please don't. It means you're going insane like me. Okay, so this step right here, second step, is going to be 31,630 joules. All right, last step right here. Last step is going to be where we take our 100 degrees Celsius steam and we take it to 150 degrees Celsius steam. And for this one, pretty simple. We're just going to use the Q equals MCAT formula. But this time, just make sure that you use the values for, obviously, for steam. So I'm going to give you guys about 3 to 4 minutes to do this. And after that, once you get your answer for step 3, see if you guys can add it all up. And that will be your final answer. And we're finally done with this insanely long problem. Okay, so go ahead, try that out. See if you can get the final answer for this. Alrighty guys, so I got the final answer for you up on the screen. For 100 degrees Celsius steam to 150 degrees, it's going to take 1397.2 joules. And then you just add the 3 numbers, you should get about 37,708. Okay? If the question asks you for kilojoules, then you would just move the decimal 3 times to the left. It'll be 37.7 kilojoules. Okay. Whoa. All right, and that is Unit 6.
Wait, solid? Oh, wait.
No one has ever mentioned that to me. Because, yeah, if it's not 97.81, it could either be fully melted or fully solid. I could even do half melted.
Half melted's fine.
Yeah, you could do half. Because then you would have to have the grams to do it.
No, the half melted. The half melted.
I'm good. That's too much even for me. I don't care enough about your knowledge.
So this particular problem.
All right, guys, I got the 2 steps up there for you if you want to just check real quick. You should have 2 steps, melting and then heating up the liquid. It's a little bit more manageable than last time, just different numbers. Oh,
Can you control the temperature in this room? Or is it...
I could, but I like keeping it cold.
I told you.
So I swear it's fine to this cold.
I do it on purpose.
Like 6. I told you just
I think it's about 6'7", 67 in here.
It is not 6'7". It's like
It's so
6.
cold, my hands hurt.
Okay, bring a jacket. I'll put a little coat hanger for you. I'll put a little nail on the wall. Just hang a coat every time you come in. It's because it pacifies the annoying kids, and also prevents the smell. It starts smelling bad in here. Yeah.
Why would we listen? Okay, so 5-minute break.
Oh shoot! I forgot we were on break. Oh, I was recording that whole time. Okay, so first step is melting because you're already at the melting point. So all you got to do is melt the solid, and the second step you turn the melted Na into 500 degrees Celsius. So you're heating it up. And so just make sure you're aware of the heat of fusion. You got to use moles. So you have to convert 5 grams into moles of Na, and then you multiply by 2.6, which is the heat of fusion. Get 565. And the second step, heating it up, is just Q equals MCAT. And then just make sure you use the specific heat for liquid sodium, because now you're in the liquid phase. And then you just add it up, and that's it.